Hi, I'm Bob. Welcome back to the tutorial on how to solve the exercises in the textbook Microeconomics Theory and Applications with Calculus, the 5th edition. We will continue our step-by-step solutions to the questions in Chapter 13, Game Theory. We are at the first section, the static games. We will adjust the next 5 problems today. Here's exercise 1.6. Suppose that two firms face the following payoff matrix. Given these payoffs, firm 2 wants to match firm 1's price, but firm 1 does not want to match firm 2's price. What, if any, are the pure strategy Nash equilibria of this game? We use the best response approach to find the Nash equilibrium. The payoff matrix shows the payoffs of the firms in each combination of the strategies. The first number in each cell is firm 2's payoff, and the second number is firm 1's payoff. We first figure out firm 1's best response to firm 2's each choice. Suppose firm 2 chooses a low price. If firm 1 chooses a low price, it gets 0. But if it chooses a high price, it receives 2. A high price is its best response. We underline the payoff 2. Suppose firm 2 chooses a high price. In this case, firm 1's best response is choosing a low price because it results in a higher payoff than choosing a high price. We underline its payoff 7. Next, we consider firm 2's best response. Given that firm 1 chooses a low price, firm 2 gets 2 if it chooses a low price, but 0 if it chooses a high price. So, firm 2's best response is choosing a low price. We underline the payoff 2. Given that firm 1 uses a high price, firm 2's best response is to choose a high price because it brings a higher payoff. We underline the payoff 6. We could not find any cell with both payoffs underlined. There is no pure strategy Nash equilibrium in this game. Let's solve exercise 1.7. What is the mixed strategy Nash equilibrium for the game in exercise 1.6? Assume that firm 1 chooses a low price at a probability of alpha. It implies that it chooses a high price with the probability of 1 minus alpha. We calculate firm 2's expected payoff. If firm 2 chooses a low price, its expected payoff, pi 2L, equals 2 times alpha plus 1 times 1 minus alpha. If firm 2 chooses a high price, its expected payoff, pi 2h, equals 0 times alpha plus 6 times 1 minus alpha. Firm 2 should be indifferent between choosing a low price and a high price. So we have the following equation and solve for alpha. It is 5/7. It means firm 1 sets a low price with a probability of 5/7 and a high price with a probability of 2/7. Why should the two expected payoffs be the same? That is because if it is not the same, say pi L is greater than pi h, then firm 2 will choose the low price with certainty. Given that firm 2 chooses the low price, firm 1 will choose a high price with certainty. knowing that firm 1 will choose a high price, firm 2 will switch to the high price. The players always have an incentive to deviate, and it could not lead to an equilibrium. Only when the firms are indifferent between their two strategies can the game have a Nash equilibrium. The same reasoning applies to the other player, and we can find beta, the probability at which firm 2 chooses a low price. It is 1/3. Firm 2 sets a low price with a probability of 1/3 and a high price with a probability of 2/3. Thus, the mixed strategy Nash equilibrium for the game is: firm 1 sets a low price with a probability of 5/7 and firm 2 sets a low price with a probability of 1/3. Let's find answers to exercise 1.8. Suppose that Toyota and GM are considering entering a new market for self-driving trucks, and that their profits from entering or staying out of the market are as shown in the payoff matrix. If the firms make their decisions simultaneously, which firms enter? How would your answer change if the US government committed to paying GM a lump sum subsidy of $50 million on the condition that it would produce this new type of truck? Since the firms make their decisions simultaneously, it is a static game of complete information. We use the best response approach to find the Nash equilibrium. In the payoff matrix, the first number in each cell is Toyota's payoff, and the second number is GM's payoff. We first consider Toyota's choices. Given that GM enters the market, if Toyota enters, it earns a profit of 10. If it does not enter, it earns 0. Toyota's best response is entering the market. We underline its payoff 10. Given that GM does not enter the market, Toyota's best response is also entering the market because it brings 250 instead of 0 if it stays out of the market. We see that Toyota has a dominant strategy of entering the market regardless of its rival's choice. Next, we figure out GM's strategy. Suppose Toyota chooses to enter. GM makes a negative profit if entering, but 0 if staying out. Its best response is not to enter the market. Suppose Toyota stays out of the market. GM's best response is to enter the market because it brings 200 profit instead of 0. We underline those payoffs. Finally, we circle the cell with both payoffs underlined. That is the outcome of the Nash equilibrium of the game. Here, we can also think of GM's strategy this way, since it knows that entering is Toyota's dominant strategy. That is to say, Toyota must choose it. GM's only choice is not to enter. The Nash equilibrium of this game is that Toyota enters the market and GM stays out of the market. The government's subsidy changes the payoffs of the game. As a result, it may alter the Nash equilibrium. We write down the new payoff matrix. GM's payoff will increase by 50 if it enters the market. So the two numbers are different from the old payoff matrix. We use the best response approach to find the Nash equilibrium. We first consider Toyota's decision. Given that GM chooses to enter the market, Toyota gets 10 if it enters the market, but 0 if it does not. Its best response is to enter the market. We underline its payoff of 10. Suppose that GM stays out of the market. Toyota's best response is still to enter the market because it brings a higher payoff of 250. We underline its payoff of 250. We find that Toyota has a dominant strategy, entering the market, no matter what GM chooses. Knowing that Toyota uses its dominant strategy, GM's best response is to enter the market because it gives a profit of 10 instead of 0 if it stays out of the market. We then circle the cell with both payoffs underlined. That is the outcome of the Nash equilibrium of the game. The Nash equilibrium is that Toyota enters the market and GM also enters the market. The outcome is that each player earns a profit of 10. We see that the government's action can change the payoffs and therefore the Nash equilibrium of the game. Let's solve exercise 1.9. In the battle of the sexes game, the husband likes to go to the mountains on vacation, and the wife prefers the ocean, but they both prefer to take their vacations together. The payoff matrix is as follows. What are the Nash equilibria? Discuss whether this game and equilibrium concept makes sense for analyzing a couple's decisions. How might you change the game's rules so that it makes more sense? We use the best response approach to find the Nash equilibrium. We consider the wife's decision first. Suppose the husband chooses to go to the mountains. The wife gets 2 if she goes to the mountains, but -1 if she goes to the beach. Her best response is to go to the mountains. We underline her payoff of 2. Suppose the husband chooses to go to the beach. The wife's best response is to go to the beach because it brings a higher payoff. We underline her payoff 1. Next, we figure out the husband's best response. Given that the wife goes to the mountains, the husband's best response is to go to the mountains because it gives a payoff of 1 instead of -1 if he goes to the beach. Given that the wife goes to the beach, the husband's best response is to go to the beach. We underline those numbers. We find 2 cells with both payoffs underlined. There are 2 pure strategy Nash equilibria of the game. Both go to the mountains and both go to the beach. The payoffs do not make sense. The wife prefers the ocean, so she should have a higher payoff going to the beach with her husband than going to the mountains with her husband. But this may be a typo. Swapping the position of the players will lead to a payoff matrix consistent with the description of the exercise. There are 2 Nash equilibria of the game. We don't know which one will happen. More information is needed. For example, if the wife makes a decision before her husband, then they will go to the beach together. Let's go to exercise 1.10. We will show the payoff matrix for the rock, paper, scissors game. What pure or mixed strategy would you have recommended and why? It is a static game of complete information. We use the best response approach to find the pure strategy Nash equilibrium. As usual, the first number in each cell of the payoff matrix is player 1's payoff, and the second number is player 2's payoff. We first find player 1's best response to each of player 2's strategies. Suppose player 2 chooses rock. Player 1 gets 0 if choosing rock, -1 if choosing scissors, and 1 if choosing paper. Her best response is using paper. We underline her payoff of 1. Suppose player 2 chooses scissors. In this case, player 1's best response is to choose rock because it brings the highest payoff. Suppose player 2 chooses paper. Player 1's best response is to use scissors. We underline those payoffs. Next, we consider player 2's best response. Given that player 1 uses rock, player 2's best response is to choose paper. Given that player 1 uses scissors, player 2's best response is to choose rock. Given that player 1 uses paper, player 2's best response is to use scissors. We underline the corresponding payoffs. We could not find any cell with both payoffs underlined. There is no pure strategy Nash equilibrium in this game. We will find a mixed strategy Nash equilibrium. Assume that player 1 uses rock with a probability of beta 1, scissors with a probability of beta 2, and paper with a probability of 1 minus beta 1 minus beta 2. We calculate player 2's expected payoff for each of her choices. If player 2 chooses rock, her expected payoff, pi 2r, equals the payoff in each possible outcome times the probability of that outcome. We compute the expected payoffs for using scissors and paper, respectively, in the same way. Player 2 should be indifferent between her 3 choices. That is, the 3 corresponding expected payoffs should be equal to each other. We can obtain beta 1 and beta 2. The same reasoning applies to the other player, and we can get alpha 1 and alpha 2. Therefore, the mixed strategy Nash equilibrium for the game is that player 1 uses rock, scissors, and paper with a probability of 1/3, and player 2 uses the same strategy. The expected payoff for each player is 0. Thank you so much for watching this video. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.